So with that, I'll introduce Avik. So Avik Dutt is faculty here at UMD, both in mechanical engineering and in the Institute for Physical Science and Technology. He just started in January of 2022. Prior to that, he got his bachelor's degree from IIT Kharagpur, I believe, in India. Then did his PhD at Cornell University in Michal Lipson's group, worked on a number of different topics on integrated photonics, sort of nonlinear optics, both looking at squeeze light generation, looking at curved frequency comb generation and applications in things like dual comb spectroscopy. And then he did a postdoc at Stanford in Shanhui Fan's group, looking at this topic he'll be describing today on topological photonics and synthetic dimensions. So with that, let me hand it over to Avik to get started.
Thanks, Karthik, for the introduction, and thanks, Karthik and Wendell, for this opportunity to talk to the audience of the JQI seminar series. It's actually a very exciting opportunity for me because I've been following the seminar series for quite a bit of time, and I'm glad that I get this to talk about some of my postdoc work in Shanhui Fan's group, particularly as a part of this seminar. And I hope that this also spurs some more discussions about, working on common ideas and collaborating with a lot of people that have a lot of common interest at UMD. So what I wanted to talk to you today is this concept of synthetic dimensions, which I'll introduce, which we've been working on for a few years, and how this can really simplify the implementations of a lot of complex topological models, or in general, any lattice models that we want to implement. And I'll show you some concepts and background, as well as experimental demonstrations of that, and how we can extend it into more future higher dimensional systems. So this is just a slide on the research group that I'm building. It's focused on experiments, but also some theory and computation on these three fields of quantum photonics, nonlinear photonics, and topological photonics, for studying both on the fundamental science side, emergent phase of light and matter, and how we can characterize or probe them, but also for applications in quantum as well as classical communications, computing, and sensing, or spectroscopy. And I'm going to be focusing on the third topic that I listed here of topological. Let's see, so it'll take me some time. Okay, yeah, topological. I'll get used to this pointer. Yes, on topological photonics, which was part of my postdoc work. And we are going to continue exploring a lot of these things in the group that we are building. So I wanted to start with not all of topology, which is a huge topic, but one specific example of topology that will come again and again in the work that I will describe here. And this is something that started around 4 decades or so ago, the quantum Hall effect and its connection with topology. So if we take a 2-dimensional electron gas and then confine it in the 3rd dimension, subject it to a very high magnetic field and take it to low temperatures, we can get some very fancy effect, which is called the quantum Hall effect. And what happens here is that the bulk of the material becomes insulating, whereas the edges of this material are conducting, and they support one-way chiral edge states. And the interesting part about these edge states is that they are immune to disorder or backscattering as long as it does not close the band gap of the system. Just because there exist no modes that go in the other direction at this energy in the system. Now, this has been studied in condensed matter physics as well as in atomic physics for quite some time. And the number of edge states supported at a certain energy is linked to a property of the bulk, a topological invariant, which is called the Chern number. And the magnetic field plays a very important role in this, because without the magnetic field, it's hard to realize a non-zero Chern number in such a system. The magnetic field also breaks something that we call time reversal symmetry in the system, and hence it can be used for implementing non-reciprocal devices which have applications in photonics. And because these edge states are immune to backscattering, they can have use for robust devices in photonics beyond condensed matter physics. So this is just a very brief introduction to topology, especially with the quantum Hall effect. And we'll come back to a bit more details later. But if you look at the photonic implementations of this quantum Hall effect or topology in general, a lot of which was actually started here at JQI itself. This is Mohammad Hafezi's early work on topological photonics. We see that they are made of very complicated structures. They are seminal experiments, but they often consist of tens to hundreds of waveguides, and they're coupled in a very precise way. We have to control the phases between the ring resonators, which were used to create this model here. And hence, we're always looking for simpler and simpler ways of realizing the same thing. And how simple can we go? From tens to hundreds of waveguides and resonators, can we go to something as simple as a single or just a pair of ring resonators and study essentially the same physics? And the answer is yes, as I'll tell you today. That's why I'm here talking about it. But also, it's important to realize that if we can simplify the implementation of the two-dimensional models that I was talking about in the previous slide, we can think of going to higher dimensions. And the general mantra in topology seems to be that higher the dimensions, richer the topology. So if we can simplify the implementation of 1D or 2D models, then that leaves a lot of room to scale up to study higher dimensions, such as the 4D quantum Hall effect, which has no lower dimensional analog in 3 or fewer dimensions, and higher order topological insulators, which have just emerged in the last 5 years or so. So that brings me to my outline, where I'll be providing an introduction to the concept and background of this concept we call synthetic dimensions, and then move into experiments where we developed a spectroscopy technique to study the band structure directly in experiments. Then we'll show how we can use this method that we've developed to study something that shows a non-trivial Hermitian topology, the synthetic quantum Hall ladder, and move on to extending it to non-Hermitian topology. And if time permits, I'll go over some other applications or fundamental things that we've been studying, again, in this concept of synthetic dimensions. If you have any questions, please feel free to stop me at any point, and I'm happy to make it more interactive instead of leaving all questions to the end. So just raise your hand, or if you're on Zoom, just shout it out and I'll try to follow up with the answer. So before we get started, we wanted to discuss what do we again mean by this concept of synthetic frequency dimensions. And I know that this might not need a lot of introduction, especially to the JQI audience, because a lot of initial work in synthetic dimensions was done here in cold atomic systems at JQI. But just to go over it briefly, if we have a 2D array of pillars, each of which has a different height, then this third dimension of height can be encoded in the form of a color of a two-dimensional completely planar array of dots. And this third dimension of color or frequency now plays the role of a synthetic dimension. Now, a lot of us might think that how is this different from, let's say, wavelength division multiplexing, where we are also encoding information in the wavelength or frequency degree of freedom. And my thought behind that is, in wavelength division multiplexing, we are treating all of these information channels in different wavelengths or frequencies as independent. But here, what we want to do is we want to harness the connectivities or make the different frequency modes coherently interact as they evolve in time. And that is what sort of sets apart this concept of synthetic frequency dimensions from just multiplexing in frequency space. And once we can build this concept of synthetic frequency dimensions using any internal degree of freedom, such as spin, polarization, mode number, or frequency, we can now study higher dimensional physics on lower dimensional geometries with much more compact spatial footprints. That's also easier to fabricate and experimentally probe. And the other thing I want to emphasize is, since modes in the synthetic frequency dimension are not coupled by how close they are geometrically or physically, but in fact, by external perturbations or modulation that we apply, it's very easy to realize long-range coupling along these dimensions. And again, I'll show you some examples of that we've realized in experiments. The synthetic dimension concept was started again in ultra-cold atoms and followed by other platforms as superconducting qubits or optomechanics. And this is work from related to the Spielmann group here at JQI from 2015. And in photonics, this concept has really taken off because there are a very large number of internal degrees of freedom we can use, such as orbital angular momentum, frequency, spatial supermodes, or time multiplexing. And every year, the number of demonstrations as well as number of platforms seems to go up at a pretty fast pace. So it's a very exciting time to be working on photonic synthetic dimensions today. The platform that we chose is to use the equidistant frequency modes of a dielectric ring resonator. And you know that when this kind of a ring resonator is completely static and it does not have any perturbations on it, the eigenmodes of the ring are separated by the free spectral range, which is nothing but the time it takes light to go around once in the ring, the inverse of that time. And these are all uncoupled and orthogonal to each other. Now, if we introduce a modulation using, let's say, an electro-optic modulator that changes the refractive index of a small portion of the ring, but at a frequency that is equal to the mode spacing, we can introduce coupling between these modes and form a 1D tight binding model with a nearest neighbor coupling along this frequency dimension. Now, this is not perhaps surprising. What is very interesting is we can get more than 100 modes or thousands of modes coupled in experiments, which is quite contrary to the other examples of synthetic dimension that were studied before. For example, the spins in ultra-cold atomic physics, where we can get, let's say, a few to maybe 10 modes along the synthetic dimension. And very recently, there have been some experiments at Cornell where they showed 100,000 modes that were coupled along this frequency dimension. So we can really probe very large lattices, effectively infinite lattices in frequency dimension encoding. Looking at this in a bit more, yes, you had a question? Yes.
So in the gray box, you have like a effective nearest neighbor hopping.
Yes.
What's the JMN on the next one?
Yes. So I should have perhaps put the question is, what is the JMN in the second line of this equation here? Yes, in the more general case, this is just nearest neighbor hopping. Yeah. So I took out the J from the summation here. But in the more general case, you would calculate the coupling between, let's say, M and a mode N that is not just nearest neighbor, but further away. Sure. And the coupling amplitude will be given by the sort of the Fourier transform in phase or the azimuthal phase angle of the perturbation that you apply to the ring resonator. So this is just nearest neighbor coupling using modulation at the FSR, but I'll show you examples where you can modulate at multiples of the FSR, and then JMN can be non-zero for MNN not nearest neighbor, let's say.
So that sync expression is a special case?
So the sync expression is a special case for this delta n phi being a rectangular function in this azimuthal phase angle. Okay. Yeah, that's a good question. Yeah, this is a specific example for rectangular phase modulation. Any other questions? Okay, so let's move on and look at it in a bit more detail. If you look at the transfer function of an electro-optic phase modulator, we can expand it in the form of Bessel functions using the Jacobi-Anger identities. And we can see that if we come in with a frequency omega naught, then the upward going modulation that produces a coupling to the mode at omega naught plus capital omega has a phase that is equal and opposite to the downward going modulation that goes from omega naught to omega naught minus capital omega. And this phase of the modulation that comes from the, let's say, RF signal, if the frequency of the modes are separated by RF frequencies, can directly be imprinted on the side bands. And this will be important in the next slide, where I'll show how this phase now plays the role of an effective gauge potential along the frequency dimension. So that was using a single ring. If we now create a 1D array of ring resonators, each of which has a modulator that is modulated at the FSR, the same frequency FSR, and they are coupled by evanescent coupling through this constant kappa. But the phases of the modulation on the different rings are linearly ramped, so as to say. Then the equivalent 2D model of the system, where the let's say horizontal axis is real frequency, real space, and the vertical axis is frequency space. If you stare at it long enough, it seems exactly that of an electron in a magnetic field confined to a 2D lattice. And so what we've done here is quite interesting. We've taken a neutral particle, such as a photon, and just by playing around with the couplings along the real and synthetic dimensions, we've been able to realize a magnetic field, an effective magnetic field for such a chargeless particle, that is a photon. And if you go ahead and look at the band structure of this system, it shows these bulk modes, shown in blue here, that are separated by band gaps spanned by the topologically protected one-way or chiral edge modes. And again, these modes are resistant against backscattering as long as the disorder does not close this band gap. So if we now go ahead and in simulations probe what will happen if we put in a single frequency on the leftmost ring through a waveguide that's coupled to the leftmost ring, we see that it first goes up in frequency till it hits an edge along frequency space. And how to create that edge is something I hope I can come to talk about towards the end of the talk. And then once it hits the edge in frequency space, it starts going right, because there is no mode that couples in the opposite direction at this energy or frequency. And then it propagates in the highest frequency mode in the rings till it hits the edge in real space, at which point it has no option but to go downwards. And this continues to form a sort of clockwise chiral one-way edge mode in this hybrid real synthetic frequency space. Yes.
Why is there an upper limit?
So there, the question is, why is there an upper limit to the frequency? And that's a question I get very often. So to answer that question, we decided to do some experiments later on and say, how can we get that upper limit in frequency? But in a general ring resonator, you don't expect a sharp boundary in the frequency dimension. And that is one of the challenges that need to be overcome in frequency dimensions. But there are ways to overcome these challenges that I'll talk about. Yes.
Because of the fact that velocity dispersion is non-zero.
Yes, so just to repeat what Mohammed said, is the group velocity dispersion of the waveguide non-zero. That will produce a boundary, but along a very long number of frequency modes, and it also will produce a gradual boundary, not a sharp boundary like I'm showing here. To produce a sharp boundary, which is what we often want in topological photonics, we have to do some more work. Yes. But the group velocity dispersion can produce, let's say, a gradual boundary. You're totally right. Yes. Thanks.
Sorry.
Yes.
Quick question. So you're also assuming that the disorder cannot scatter between frequencies.
Yes, that is right. And actually, scattering between frequencies is very easy to prevent, because it would need to produce some energy or some dynamic modulation to couple different frequencies. So in some sense, the frequency dimension lattice is more perfect than most real dimension lattices. This needs a lot of work to actually couple between different frequencies. Any other questions? Okay, so now let's look at something that we found interesting while studying this frequency dimension. And that comes to the next topic of band structure measurement that I'll discuss. We know that any periodic system, this is from our undergraduate 101 solid state physics course, any periodic system is described by a band structure according to Bloch's theorem. Be it electronic systems, where the band structure tells us whether something is a metal or an insulator depending on the band gap. The band structure also encodes topology in the eigenfunctions. In photonic crystals, it tells us whether certain frequencies are allowed to propagate in the system or completely blocked from propagating in the system. So in general, the band structure plays a very important role in describing the properties, the transport, as well as the topology of a system. So we started asking this question: what does it mean to even have a band structure along the frequency dimension? So to answer that, we can take again our, let's say, simplest 1D tight binding model with nearest neighbor coupling, and then go to block wave number space by taking a Fourier transform. And we see that the band structure or the Hamiltonian is diagonalized to produce a band structure that looks like a cosine. And this cosine has an amplitude that is proportional to the strength of the coupling J between these nearest neighbor modes. So in real space, we know that the X is separated by this lattice spacing and periodic in A, the lattice spacing, and the reciprocal space is periodic in 2 pi over this lattice spacing A. So that's 2 pi over A again here in K space. And this reciprocal space is conjugate to X. So if we have a synthetic frequency lattice whose real dimension is effectively frequency separated by the FSR capital omega, then the reciprocal space must be conjugate to frequency, and the physical quantity that is conjugate to frequency is nothing but time itself. And this turns out to be periodic in 2 pi over the lattice spacing capital omega. And this has a very interesting interpretation, that if we now make a connection, the block quasi-momentum K has a 1-to-1 link with the time t in units of the round trip time. So this means that if we excite this modulated ring resonator with a waveguide and sweep the frequency of the input laser, we can actually calculate the drop port transmission here. And if we can measure this drop port transmission while sweeping the input laser frequency at time scales that are much faster than the round trip time of the ring, this is full wave simulations in the Floquet picture, showing that we can completely reconstruct the band structure by looking at the peaks in the transmission. So we get a cosine band structure for a 1D nearest neighbor model. And we wanted to check this in experiments. So we built a system consisting of a modulated fiber ring cavity with an FSR of around 15 megahertz. So it corresponds to around 13 meters of cavity length. And the important part of this cavity is a lithium niobate electro-optic modulator with a bandwidth of around 2 gigahertz. And on the detection side, we had a 5 gigahertz in-gas photodiode and a 1 gigahertz oscilloscope followed by Fourier transform. So this 1 gigahertz bandwidth allows us to accommodate a large number of frequency modes that are separated by 15 megahertz in the detection side. And we are very excited to see that when we actually go ahead and measure the time resolved transmission, the band structure looks exactly like what we would expect from a cosine theoretical prediction. So I'll walk you through this video here, where on the left, we are plotting the detuning of the input laser from one of the frequency modes on resonance. And on the horizontal axis, we have the time either in normalized units here, or on real units, nanoseconds here. And as we see, the laser detuning sweeping through the different resonances or the bands of this modulated ring resonator, we see peaks in the time resolved transmission exactly where the detuning crosses one of the bands of the modulated ring resonator. And when it's outside of these bands, we see a pretty flat transmission. So by vertically stacking these time traces, we can completely reconstruct the band structure of such a frequency dimension lattice. If you would allow me to stretch this a bit, this is something like a photonic analog of RPS for the condensed matter experts in the audience. But again, in frequency lattices, we can do it in a completely time resolved fashion. Now, the other interesting thing about synthetic dimensions is that we can tune the strength of the coupling at will without having to change the structure. So I'm showing an example where we go from completely uncoupled bands, showing Lorentzian resonances, when we apply no voltage on the electro-optic modulator, to something that has either moderately cosine bands or something that has a very large bandwidth in terms of the band structure. So here the coupling is pretty strong because the width of these bands is larger than the FSR that we have in this system. Now, all of this was done using a fast photodiode. If we now replace this with a slow photodiode, what we see is not the band structure, but the density of states, because the K domain information gets averaged out. And so we can go from Lorentzian resonances just because of the finite lifetime of the photon in the cavity to something that matches the theoretical predictions shown by the red dashed lines very well. And the edges of these bands, we also see the Van Hove singularities, which are typical of periodic systems in different dimensions. So this is for a 1D system. This means that we can not only measure the band structure, but also the density of states directly. If we keep extending this idea, we can not only do nearest neighbor coupling, but also add on the same electro-optic modulator. So we do not change the complexity of the system, we just change the time domain signal we are applying to the modulator, and let's say add a modulation at twice the frequency of the FSR. We also can add a phase between the nearest neighbor hopping and the second nearest neighbor hopping. And it turns out that this phase again gets imprinted on the frequency domain lattice. So the upward going modulation shown by the blue arrows produces a phase of phi, and the downward going modulation shown by the pink arrow produces a phase of minus phi. So we can rearrange this lattice in the form of a triangular array of plaquettes, which are now threaded by alternating magnetic fluxes in this lattice. We went ahead and measured this system, and again, we saw that the theoretical prediction matches very well with the experimental observation we had. In this band structure, we see something that proves that we can also get non-reciprocity, because if you look at the plus k bands, it is not symmetric with the minus k bands. So by extending this idea, we can look at applications in non-reciprocal frequency translation, again using one or more longer range couplings with the right phases that we want. Any questions up to this point before I move on to going beyond 1D on Zoom or in the audience here? The spatial dimensions of, so the question is, what are the spatial dimensions of the object? In this system that we built, it was around 15 meters in ring length, but you can always compact that into, let's say, a few centimeters radius of spool in fiber along with the components. But there have also been experiments by several groups that have shown nanophotonic integration, so we can make this in the form of centimeter scale waveguides on chip, let's say. Yes, thanks. Question.
So in the previous slide, you said that you can make sort of any kind of coupling by cleverly modulating the phase. I was wondering, like, what are the constraints on it? Like, can you make any network, like sparse network, long range interacting network, anything? And then how do you get these couplings if I give you a network structure?
Because the question is, can we make sparse networks or more arbitrary networks with different kinds of long range coupling? And how do we design that? So I should say that the frequency dimension encoding does have some symmetry constraints, in the sense that if we do it in the most naive way, then the V1 that couples, let's say, M to M plus 1 is also the same value that couples M plus 1 to M plus 2 within a, let's say, range of frequencies. But then you using additional structuring on the ring resonator, or by coupling more ring resonators of different lengths, you can, let's say, either inverse design or engineer the couplings between more further separated modes. That's definitely more complicated than the simple system that I'm showing you here, but there is a route to do that. And Karthik's, Srinivasan's group here has been looking into some of those more, let's say, structured ring resonators, how one can get more flexibility in terms of the coupling that we can get beyond, let's say, the bare symmetry that the system enforces. Well, that's a very good question. Yes?
Modes are not equally spaced frequency. Would you see the effect of that in
Right. So the question is, if the modes are not equally spaced in frequency, yes, you'd see that in terms of either effective potentials, local on-site potentials that show up in the model. Yes. Right. So all of this was in 1D systems. Yes. Can you? So yeah, that's actually a very interesting question. What happens if you put nonlinear crystals in this ring resonator? And then you can get models which not only have linear coupling, but let's say higher order terms, depending on the strength of the nonlinearity. The question is whether you're looking at that in the classical regime or the quantum regime, and then again, the manifestations can be different. Yes.
So is the right hand one, is it reciprocal or not?
The question is, the right hand model is reciprocal or non-reciprocal? That is symmetric in K, so that is reciprocal for this phase of pi.
But you can see that in the black curve and the yellow curve.
That is just experimental, let's say, slight uncertainties. Yeah. Okay, so let's move on to going beyond 1D lattices. And for that, we decided to use another synthetic dimension, that is the same ring now supports not only a clockwise mode that has a frequency synthetic dimension, but also a counterclockwise mode where photons can go around in the same frequency in the opposite direction. And we refer to this as a pseudospin dimension for this ring resonator, in addition to the frequency dimension. So we know that the frequency dimension can be coupled using an electro-optic modulator, and the clockwise modes shown by the blue dots can be coupled to the counterclockwise modes shown by the red dots here, using this figure of 8 coupler that we introduced. And if you look at this in a bit more detail, we can see that if a clockwise photon comes in through this directional coupler here, it goes into this blue arm and then goes around and comes out with a phase that is dependent on the length L1, but now in a counterclockwise mode. On the other hand, if you have a photon that comes in a counterclockwise mode, it will go into this directional coupler, into this pink dashed arm, and come around as a clockwise photon. So that is shown by the pink right to left arrow here. Now, if we make the lengths L1 and L2 different, then the phase going from left to right or clockwise to counterclockwise is different from the phase of the photon going from right to left or counterclockwise to clockwise. What is perhaps even more important is this phase difference is dependent on the length difference in a linear way. So if you are sitting at a frequency that is m, the phase difference that we accumulate is different from the phase that you accumulate if you're sitting at a higher frequency, let's say m+2. So this automatically realizes a model that I showed you before, which is a real coupling along one of the dimensions and a linearly ramped phase along, let's say, the vertical dimension here. So it's, again, a very simple system, a single modulated ring resonator with just an additional figure of 8 coupler that can now realize something that would typically require, again, tens to hundreds of resonators in the most naive implementation. And this speaks to the scalability of realizing models using synthetic dimensions. This is not the first time what we call this a synthetic quantum Hall ladder was implemented. It was done a few years earlier in bosons using 2 real dimensions, or fermions and bosons with 1 real and 1 synthetic spin dimensions, again by the Spielmann group here. But our implementation was the first where we do not need any real dimension here. We have just a single ring resonator, not an array of ring resonators, and we can use 2 independent physical synthetic dimensions to realize the same physics. Going into quantum Hall systems in a bit more detail, we know that they're typically extended along the x as well as y dimensions, and they form a 2D square lattice of some sort. And they have, again, bands which are shown in blue, the bulk bands, separated by the band gaps traversed by chiral edge states that are localized on the left or the right edge, if you assume that the vertical direction is infinite here. And the number of edge states is related to a quantity that can be calculated from the eigenfunctions of these bands. And this turns out to be an integer called the Chern number, and it's related to the k-space wave function phase binding. I'll come back to this later when we discuss non-Hermitian topology, but for now I want to emphasize that this is calculated from the wave functions, not the energies of the bands, because the wave functions are usually complex valued. Now, what we have in our system is not an extended system along x. We just have 2 sites along x. So do we still see any manifestation of this chiral edge states or topology? And the remarkable answer turns out to be yes. We indeed do see that even in just a 2-site system or a 2-leg ladder, the bulk bands are completely erased, but the edge modes still survive. And this is something that was predicted by Hugel and Paredes in this paper in 2014. But we see that even in this extreme perturbation where we're removing all of the bulk sites, because the parent model has strong topological protection, we see that the edge sites survive, or the edge modes survive this kind of a strong perturbation. Yes, there was a question. All right, yeah. So how can we measure this? To measure this, we look at a spin and momentum resolved band structure measurement, where the momentum resolution comes from the time resolved detection, and the spin resolution comes from the fact that we can either excite from the left into the clockwise mode and then detect on the right to get the clockwise projected band structure, or do the opposite for the counterclockwise projected band structure. So we have control over measuring in both spin and momentum resolved fashions. And we were again very excited to see that the experimentally measured bands agree very well with theoretical predictions as well as full flow case simulations. And we see these one-way nature of the bands because of the asymmetry in case space. We also see that a few other phenomena show up. If we write the Hamiltonian in K space, then we can write it in the form of something that shows spin orbit coupling, where the K dependent magnetic field is coupled to the spin degree of freedom, the clockwise counterclockwise degree of freedom. And this leads to spin momentum locking, because when we look at the positive K bands, they are primarily localized on the clockwise modes, whereas the negative K bands are localized on the counterclockwise mode for the lower band. So we are seeing spin momentum locking arising from spin orbit coupling in this kind of a structure. We can again tune the strength of the coupling along the frequency dimension by changing the voltage we apply on the electro-optic modulator, and we can go from a regime where there's a single K minimum to a regime where there are 2 K minima with strong asymmetry in the band structure. And again, if we stretch this a bit in atomic or superconducting systems, this has been called a Meissner phase to vortex phase transition. And although we are not seeing the manifestations of interactions in the system, at least we see the manifestations in the band structure that we measure. Now, all of this was done in a reciprocal space through K space measurements. We can also look at the same thing in synthetic lattice space. And for that, we can define a chiral current that if we excite the left edge of the ladder, it will primarily go up in frequency. Whereas if we excite the right edge of the ladder, it will go primarily in the downward direction in frequency for a certain band. And hence, if we measure the asymmetry using, let's say, an acousto-optic modulator that heterodynes the cavity output with the input laser, we can directly measure the lattice space occupation. And the simulation here shows that we can indeed see a one-way propagation if we excite the left leg of the ladder. So we went ahead and measured that in experiments, and we again saw that if we focus on this lower band energy here, we can indeed get a distribution in frequency that is asymmetric. And if we now switch the direction of the magnetic field by just going by changing the length of the arms that I mentioned before, we can change the direction of the magnetic field and get the opposite kind of asymmetry in the frequency dimension. So this is effectively the same as changing the magnetic field, effective magnetic field in this lattice. So all of that was based on Hermitian topology. We've started looking into non-Hermitian topology in more recent experiments, which leads to new kind of topology that has, again, no Hermitian counterparts. So I wanted to briefly discuss what we mean by this. Usually, when we look at topology, we are looking at the phase winding of a complex function when you go around in a circle. That's one of the ways of looking at a topological invariant. And in Hermitian systems, the bands are always real valued, the energy bands. But in non-Hermitian systems, we can have complex valued energy bands because of the nature of the matrix that usually results from such a non-Hermitian Hamiltonian. There are two kinds of non-Hermiticity that I quickly might describe. One is that if you have complex valued diagonal components, then that is a non-Hermitian model that might not necessarily have topology. But if you have this other kind of non-Hermiticity where the amplitude of the coupling from left to right, mind you, not the phase, but the amplitude actually is different from the amplitude of the coupling going from right to left, we can have a non-trivial winding of the energy bands in real and imaginary energy space. And this can be quantified by an integer described in this complex energy plane. And if you look at this, topological invariant is defined in terms of the energy bands and not in terms of the eigenfunctions that we are looking at for the quantum Hall ladder. How do we do that in experiments? We can do that by simply adding an amplitude modulator in the same ring where we had a phase modulator. So this is rather trivial for us to do. And in real space, if we look at the analogy, it's significantly more complicated to create a non-Hermitian or directional coupling in amplitude. So if we go through the coupled mode equations, we see that just by adding an amplitude modulator that is pi/2 offset from the phase modulation, we can get very directional non-Hermitian coupling in these models. And one of the interesting manifestations of this non-Hermitian topology is the non-Hermitian skin effect, which has attracted a lot of attention in the last 5 years, where a macroscopic fraction of the eigenstates are localized at the edge. So it's not 1 or 2 or a few microscopic fraction of the edge states, such as we see in Hermitian topology, but macroscopic fractions of the eigenstates are now localized on the edge. In some cases, you can have almost all of them localized at the edge. So we can measure this non-Hermitian winding using the same band structure spectroscopy, but now you'll see that the bands are not just varying in the peak position, but also in the width of the band. So if we measure not only the peak position shown in the top sub panel here, but also the width of the band by fitting a Lorentzian at each k, we can extract both the real and imaginary parts of the bands and get almost arbitrary winding patterns by choosing the right modulation frequencies and phases. So in this case, I'm showing a figure of 8 winding that has both +1 as well as -1 winding number, depending on where the reference energy is set in the complex energy plane. And we can also create a very wide variety of windings. So we can get values that are larger than 1. We can get a winding value of -2 if we choose a combination of nearest neighbor and long range coupling with the right phases. And I'm not going into more details on this, but we also can look at other mathematical structures beyond windings, such as braids and knots. And it's very interesting to see those in the form of energy bands, as opposed to ropes that we would usually think in terms of knots. And such things have been looked at in optomechanical systems, in cavity optomechanical systems at Yale, where they were also able to see non-abelian braiding. What we were able to see was more abelian braiding between different energy bands. So again, we are just scratching the surface in terms of non-Hermitian topology in these experimental systems. So let me see. So I have a few more minutes. So I'm going to switch gears and talk maybe a couple of slides in terms of applications, and then if time permits, go into boundaries that had a lot of questions that came up during the talk. So in terms of linear transformations, the typical way to do that in photonics, it's nothing but a matrix vector multiplication, is to use a mesh of Mach-Zehnder interferometers. And very briefly, the number of controllable elements as well as the spatial footprint of these Mach-Zehnder interferometers to realize, let's say, an n by n matrix multiplication or unitary transformation is of the order of n squared. So if you have n modes at the input and n modes at the output, we need of the order of n squared elements as well as spatial footprint. We were able to come up with a proposal where if you use an array of n rings, not n squared rings, where each of these n rings now support n frequency modes, we can reduce the complexity from n squared to n in terms of number of control signals as well as the spatial footprint. And what we're doing here essentially is transferring the fabrication complexity of n squared Mach-Zehnder interferometers into the goal of engineering the time domain waveform that can represent the same matrix. And with a very few rings, in fact, we can get very high fidelities depending on the matrix that we want to implement. And this can also be used for non-reciprocal frequency conversion over very wide frequencies using more experimentally feasible modulators such as tens of gigahertz experimentally feasible modulators can produce wideband terahertz level frequency translation if we can engineer the couplings in the right way. Was there a question on Zoom? Okay, never mind. And the next thing that again lays a lot of questions was about boundaries in frequency dimensions. So I'm going to spend the last part of my talk discussing that. And the question here is very important because boundaries are of paramount importance in topological photonics, be it for conventional topological insulators such as 2D surface states in a 3D insulator, or even for higher order topological insulators where the edge states or surface states might be more than one dimension removed from the bulk that hosts them. So our platform, if we use a single ring resonator, usually has an equidistant array of modes that are separated by the FSR. We can introduce a boundary here by incorporating a ring with a much smaller FSR. Let's say I'm showing an example where the FSR is 6 times smaller than the main ring, and that creates coupling between the small rings modes and the main rings modes every 6 FSRs apart. And this kind of coupling will create a dispersive splitting between the symmetric and antisymmetric supermodes of these rings. So this is one way of doing this, which was more amenable to off-chip implementations, but Karthik Srinivasan's group here has been also looking at ways of perturbing the circumference of the ring resonator to create similar kinds of splittings in a more suitably engineered way. If you look at a zoom in of the spectrum here, we can see that without an auxiliary ring resonator, we have this orange mode here, whereas with an auxiliary ring resonator coupled, we can create a splitting that is much larger than the line width of the ring resonator. So we can actually create a boundary because the modulation at the FSR cannot couple these modes that are split by the auxiliary ring resonator. And we can see that in experiments as well, in terms of a spectrum without an auxiliary ring resonator and a spectrum with an auxiliary ring resonator, we see that we have bunches of modes that are separated by the FSR of the auxiliary ring resonator, and this can be now thought of as a finite lattice in frequency space. If we go and measure this, we see that without an auxiliary ring resonator, the input frequency spreads into a very large number of modes, here more than, let's say, 30 modes. Whereas if you put in the auxiliary ring resonator, it gets limited to a finite number of sites that are separated by the FSR of the small ring resonator divided by the FSR of the larger ring resonator. I think here it was split by around 14 modes or so. The other thing we see here is the top spectrum has almost no fringes. It's a very smooth spectrum because there are no boundaries to reflect the wave back. Whereas in the bottom case, since the boundaries can reflect the modes back in frequency space, we see fringes that show up because of the interference of the forward and backward going waves. And this is also clear from a line cut where you can see a smooth distribution in frequency for the unbounded ring resonator, whereas for a bounded system, you not only see a very sharp truncation of the frequency mode occupation, but also fringes that are there within the truncated number of modes. So I hope this answers some questions as to how to introduce frequency space boundaries. We also implemented this same thing in quantum Hall ladder, which shows topology. And the important thing here is that we can see topologically protected edge mode propagation in the presence of boundaries. And we don't see any fringes here, as you see in the orange line cut here. But in the trivial phase where we do not have non-trivial topology here, you can see that the fringes are pretty sharp and the excitation moves in both directions, whereas in the topological case, it only moves in one direction. So to leave more time for questions, I'll skip some of the ending slides, but just comment that we can combine quantum sources with frequency and higher order modes using either nonlinear optics to show frequency domain interference. And this relates to a question that came up about how can we create coupling or let's say imperfections in frequency modes, we can have to work pretty hard in terms of either using nonlinear optics or electro-optic modulation to actually couple different frequency modes. In this case, we harnessed it to create Hongo-Mandel interference in the frequency domain. And this was work done in Alex Gaeta's group. It's a collaboration. We can also do the same with transverse spatial modes, where you input different single photons in a multimode waveguide and get again high visibility quantum interference depending on the ratio of the coupling between these modes. I'll skip this slide on temporal modes, which we've also been looking at along with some related work in Ido Vox's group here. But the idea is that apart from frequency dimensions, which I spent almost the entire talk on, there are higher order spatial modes and temporal modes, which can also be used for very interesting things such as deterministic quantum computation or for non-local dissipation engineering. And I'll end with this summary slide where we've started to show some proof of principle demonstrations in 1 or 2 dimensions, but there's a lot of potential in extending to higher dimensions beyond 3D in a combination of real and synthetic space. I'm listing some of the ways to do that. We definitely want to move towards on-chip integration using different materials that allow for electro-optic or nonlinear optic modulation. And all of this was looking at mostly non-linear physics, but the inclusion of nonlinearities would produce a rich variety of effects, some of which would be very interesting to observe. And we've just started to scratch the surface in terms of nonlinearities and non-Hermitian topology. And I hope that I have convinced you that quantum and classical analog simulation of high dimensional physics has a lot of potential in synthetic dimensions. And we'll be looking into many of this in the experiments that we are building here at UMD. And the versatile and flexible tunability that we can get with synthetic dimensions is not so easy to get in a lot of other platforms. So we are very excited about pursuing this line of research. If you want to know more details, please check out these references and feel free to ask questions right now. Thanks a lot for your attention in person as well as on Zoom. And I can take as many questions as time allows. Thank you. Start with
So towards the end of discussing the demonstration of tricking or parameter space by introducing boundaries via adding these additional micro-ring resonators. So my first question is, if you introduce additional rings of varying sizes or varying shapes, would you expect the boundary to be even further restricted, or would it more of an interference having these almost periodic or non-analytical domains of the parameter space available, and would such a thing be beneficial for what you're seeing?
Okay, that's actually a very good question. To repeat the question, would the inclusion of more and more auxiliary rings produce, let's say, things that are beyond the domain of analytical modeling or other effects that can be seen? And I definitely believe the answer is yes. One can create either disorder or quasi-periodicity in the model, in the lattice space, using more and more rings. Now, we have to be a bit careful that, let's say if we have a ring with 2 rings with commensurate frequencies of the ratio of the FSRs, I mean. So one is, let's say, 6 times smaller than the main ring, and the other is, let's say, 9 times. We would definitely see interference effects every, let's say, 18 modes, because 6 and 9 have that as the lowest common multiple. But we can find ways of either using that to our advantage, depending on the model that you want to realize, or we can definitely engineer things so that we avoid such kind of coherent interference effects to get disorder or quasi-periodicity. But that's a very good question. Thank you. Yes.
Since towards the end of the talk, sorry, I missed it.
Yeah.
About topological protection.
Yes.
Naively, for example, P have bond and edge, and then it's set and disorder, it can be protected.
Right.
So here I have one object. So naively, I would say that if I have any disorder in that object, it would be very non-local.
Right.
So what kind of disorder the object can be robotic.
Okay, yes. So the question is, what kind of disorder do I mean that this is protected against? Because it's a single object, and any kind of disorder in the ring would indeed produce a non-local disorder that is much more long range. The specific disorder that not disorder, but the specific robustness we're talking about here is that it does not get reflected from boundaries even when we introduce the auxiliary rings. So that is not related to so much disorder, but let's say defects, because the auxiliary ring is effectively introducing a single point defect in the frequency lattice space. In terms of adding other kinds of disorder from which we can show topological protection, we do have to work hard compared to real space lattices to introduce defects or disorders. And to get local disorder, we might have to do something that is beyond perturbing just the cross section or the modulation. We indeed looked at some examples. If we can get some disorder using disorder in the time domain signal, we apply to the modulator, but that again produces the kind of non-local disorder that you're mentioning. So that is, I think, something we need to look at it in a bit more detail in terms of other ways to create disorder in this frequency lattice, either to show examples for device applications or just to implement models with disorder in the physics sense. Yes. But if you have any more ideas, please let us know what kind of disorder we can look into the system. Yes, yes. Yes, yes. Right, right. Yes.
But that was with the spin that in this
Mhm.
kind of dimension. They had some, but again, over there is the understanding of robustness.
Yeah. Was it the talk by Anusha Chandra? Or? Yeah, I remember I attended that talk. So I think that is a slightly different frequency lattice, because there it's a spin that is periodically, or let's say quasi-periodically driven by two incommensurate frequencies. And the disorder that he talked about was, I believe, in the temporal waveform you apply to the spin, right? Because that's again a single system. Here we actually have modes that are separated by the FSR, so all of those are resonant modes, unlike the periodically driven spin system. So it might be a bit different, I think. I think the integer is again the Chern number itself in the effective 2D Hamiltonian system, but the protection they talk about is with respect to the two things. If they have irrational ratios of the driving between the two frequencies, and if one looks at long-term evolution, then it's topologically robust to, let's say, some noise in the drive, is my understanding. I don't know if that's correct. Yeah. Yes. Yes. Yeah. So as Alicia is saying, it's also more, it has an inbuilt electric field throughout the lattice because of the lattice in photon number space, not longitudinal mode. So it is a Chern insulator model, but with some slightly different electric field built into it. Yeah. Yes.
That means that the locality there is not linear in the coupling. You add one photon at a time. You don't have 5 photons together.
Yeah.
Yes.
So sort of the one photon at a time, and the non-reciprocity is the photons go steadily from one drive
Yes.
mode into the other one.
So the disorder would be by that.
Yes. Yeah, that's.
So also the temporal.
The way that I drive here.
Yeah, let's say we have noise in the amplitude or frequency of the drive. It's robust to that. If you look at long-term evolution, the quantized pumping still goes through. Yes. Maybe you had a question first. Yes.
Oh, okay, I can ask. Since you can like design all these arbitrary interactions in your frequency lattice, and also in principle you could have nonlinearity, like you were saying, it seems like you have all ingredients for classical neuromorphic computing, the simple types like the reservoir ones. So what are you looking towards that, or are you looking towards that?
Okay, so I'll repeat the question. The question is if one can, since we have the ingredients for couplings as well as nonlinearities we can introduce, are people looking at neuromorphic computing in frequency space? And I believe the answer is yes. There are some groups looking at that. The nonlinearity that we get typically is, though, again, non-local, just like disorder, because all of these frequency modes are co-located within the same waveguide or ring resonator. So anything that the engineering, the nonlinearity is something that requires a lot more work than real space. So if one can find a way of, we've been thinking of ways of doing that, of creating nonlinearity that is more local and designable, then that would have a lot of impact in terms of realizing, let's say, classical unconventional computing models in frequency dimensions. Yes, maybe a question.
Talking about the boundaries and perhaps data, is the dispersion a consideration at all, the fast dispersions?
Yeah, so we did some, the question is if dispersion is a concern or not. And at least in the experimental regimes we were operating, dispersion was not a major concern. We could definitely go to, as we said, 100,000 modes without being too limited by the effects of dispersion. But one can do two things. Either one can engineer the dispersion to be much larger by using maybe concentric rings of some sort, or very specific cross-section engineering of the waveguide. And then those dispersion effects would come up much sooner than what we are seeing in our systems. The other thing is, these are fibers. When we go to on-chip systems, then dispersion will play a role sooner than in these weakly guiding and let's say large fiber systems. So definitely dispersion is something we need to take into account then. Yes. Yes.
Okay, so I'm curious about just these frequency meters on their own, and I know very little about topologies in advance. It's just a hollow tube, right? That you like.
It's an the question is what the ring resonator is.
Yeah.
It's an optical fiber that is coupled back onto itself.
Okay.
So it's let's say low index core surrounded by high index core surrounded by low index cladding that guides the light through the refractive index mechanism. Yeah.
Okay. So then that as a like as a kind of non-linearity that what you were talking about, that optical fiber has like non-linearity in it. That's also a way to engineer your interactions.
Yes, the optical fiber here definitely does have non-linearity, but it's very weak.
Yeah.
And because all the frequency modes are co-propagating in the same space, the nonlinearity would couple a large number of modes together. It's not taking two modes at the time at a couple. Even without the driving, the nonlinearity can couple the modes, but it's very weak, number one, and number two, it's coupling all the modes through cell phase, cross phase modulation, and four-way mixing. A large number of them are momentum conserving, so it's non-local. It's highly non-local. Yes. Yes, exactly. Non-local in mode number.
Okay.
Yes.
Okay. And so engineering wise, there'd be nothing stopping you from like using fibers with more non-linearity, right?
But I would say instead of using fibers with more nonlinearity, we would be better off going into on-chip ring resonators, which just because of spatial confinement and materials have a much higher nonlinearity.
Okay.
Yes. Yeah. Yes.
What's the physical origin of this magnetic field?
So the question is, what's the physical origin of the magnetic field? I would frame it in a slightly different sense, that the effect of the magnetic field on an electron is to introduce this non-reciprocal phase. Okay, so we are not creating a magnetic field for photons. We are creating the effect that magnetic fields have on electrons and creating an analog of that for photons by introducing these phases. And the biggest impact that magnetic fields have on electrons is to introduce this Aharonov bomb phase. So we can realize the effect of an electron on of magnetic field on an electron, but do that for a photon, then it's this about the same as doing a magnetic field for a photon.
So what's the effect of it copy?
So the effects that it would copy is other than the topological or quantum Hall effects I talked about, One could create circular orbits for photons in a lattice, just like if you're an electron going in a magnetic field, it exhibits cyclotron orbits. You can do something like that for photons by engineering the phases correctly. You can get circular orbits, cyclotron motion. Yeah. Any questions from Zoom before I guess?
Okay, one more question from the audience.
Yes.
So if you FM modulate and modulate, you're going to control a whole element phase. What kind of effects do we have on this?
Yes, so the question is if you have looked into modulating the modulation signal, right? So that would be done on a longer time scale than the amplitude and phase modulation frequencies, and we're definitely looking into that. One manifestation of that would be the lattice would then be changing as a function of time. The other impact of that is we've looked into either these periodically or quasi-periodically driven spin systems as an example. The other thing I can say is we've also seen we can use longer range or lower frequency modulation to create other models such as SSH models. So there's definitely a lot of things you can do, either dynamical changing of the lattice. You can do phase transitions because the lattice is changing as a function of time. So all of those are possibilities if you modulate the modulating signal. So that's a very good question. Thanks.